Okay. Okay. Then, good morning, everyone. Today we have Professor Rudnei Ramos from University, the State University of Rio de Janeiro, Department of Theoretical Physics, and he's going to speak about some recent developments in war inflation. Okay. Professor is an specialist in inflation, particularly war inflation and related topics. And we are very glad to have you here, Professor, and for this opportunity to know your work on these topics. And then you have the word, please.
Okay, thank you very much for the nice introduction. I would like to thank Giovanni for the invitation to give this seminar. So in this seminar, I intend to present some of the work that I have been doing for quite some time now, which relates to extensions of cosmological inflation in a context that tries to fully integrate the microphysics of particle and quantum field theory in the dynamics of inflation. So this approach is what we call warm inflation, which I will define more precisely in the next slides. So these are okay. So this is the plan of my talk. We will first explain what's the difference between the standard inflation scenario that we called cold inflation compared to what we called warm inflation. So after that, I'm going to explain how we actually construct this warm inflation scenario. It's based on quantum field theory, so how we have some model building machinery to make this work, this scenario to work in general. And after that, I'm going to present you how we compute the cosmological perturbations, the primordial perturbations in the context of warm inflation, because we want to compare, for example, with observations, right? So we need to compute what we can predict from this scenario. So what's the observational quantities that we can compare with, for example, quantities obtained from CMB, Planck, and other experiments on CMB, for example. So after that, I'm going to then present these observational predictions that we have in the context of warm inflation and a summary about what I have presented. So this is the general outline that I intend to present for you today. So let me just briefly remind you about the standard inflation scenario, right, that we have in cosmological inflation. Inflation is basically this early phase of accelerated expansion, usually determined by some scalar field that we call the inflaton. And when the energy density of this scalar field dominates, you basically enters in this quasi-de Sitter exponential expansion for the scale factor of the universe that is given then by an accelerated expansion and with an equation of state dominated by a negative pressure, right? That is a quasi-de Sitter type of expansion that we have then. And inflation is actually a kind of window into high energy. Because if you look, for example, at the scale where inflation happens, that is given, for example, in terms of the potential for this field for the inflaton, it can be related, for example, to an observational quantity that is this tensor to scalar range, that is the range between the tensor perturbations divided by the scalar perturbations. That is, in principle, is a quantity that can be measured. And in the most recent observations, we actually have an upper bound. It's not observed so far, but we have an upper bound for that. So that puts inflation in a scale that is close, for example, a good scale, a grand unified theory kind of scale, for example. So the first question that we must ask is whether inflation can be embedded somehow in a fundamental theory, for example, in a boot theory or string theory. So there are many different models for inflation that tries exactly to implement this, how exactly we embed inflation into a fundamental theory. And of course, when we do that, we also need to know how this field, right, the influence interacts with all the other fields in this fundamental theory. So in the context of code inflation, we have a scenario like this. You have this phase of inflation, or the potential for this scalar field dominates. So the universe enters in this quasi de Sitter exponential expansion for the scale factor. And during this phase, if you have any pre-existing radiation, it just goes away, right? The red shifts very fast with the exponential expansion of the universe. So any pre-existing radiation essentially just dilutes away. And at the end of inflation, at some point, this potential becomes subdominant compared, for example, with the kinetic energy. And the inflation ends then. At the end of inflation, you have an universe that is essentially a universe that is free, almost free of particles, no radiation. But you have to connect this end of inflation with the usual standard model of cosmology, with the Big Bang cosmology. So you need to produce a radiation-dominated regime. So this is what we call the reheating in inflationary dynamics in general, is this process of how the energy density that was inside this potential for the influence is going to essentially to radiation particles, right? It's going to decay to radiation. So this is the process that we call preheating that happens at the end of inflation. As the influence field oscillates around the bottom of this potential, this generates particles, and these particles essentially connects then with the Big Bang cosmology. And afterwards, this goes to matter-dominated regime and so on. That is a standard cosmological evolution that follows afterwards inflation. So you have then a universe that supercools during inflation. That's what we call cold inflation. And essentially what we have here, that all the influence interactions with any other degrees of freedom becomes only important at the very end of inflation, right? During this reheating phase, where this influence field has to decay to light particles to connect with the Big Bang cosmology. And essentially it's not important during all the inflationary dynamics that's happened before that. So that is what we call the cold inflation scenario. And one important signature that we have here is that all density perturbations that is going to give signatures in the CMB, for example, is generated by quantum fluctuations of this influence field. So this is the source, these quantum fluctuations of the influence field is the source of density perturbations that is going to be connected with observations like the one when we measured the CMB, for example. In the context of warm inflation, is a little bit different. In warm inflation, we have, for example, still have inflation, right? But all those degrees of freedom that were neglected during inflation, we now take into account during the inflationary regime. They are important. So these interactions of the influence with other degrees of freedom are important during inflation. And this generates, of course, dissipation and viscosity terms. There are this particle production happening during inflation, even though the radiation energy density produced during this phase of inflation can be much smaller than the energy density of the influence field. They're still important. They can be still important and influence, for example, the observables that we compute during inflation. So in this case, you have a small fraction of the vacuum energy density being converted to the radiation. And you can, even though that's a small fraction that's being converted to radiation, you can go smoothly to the Big Bang radiation-dominated regime afterwards. So you essentially don't need this separate regime of radiation. After warm inflation, you can go automatically to a radiation-dominated regime. So afterwards, it's the standard Big Bang cosmology that is we understand very well. So that's the main difference with cold inflation. In warm inflation, we essentially is taking care of all the interactions of this influent field might have with other degrees of freedom, and how this back reacts on the influent dynamics end up being important. That's what we essentially study in warm inflation. We have an earlier review about this, and this is a most recent review that all these details, you can go there and check for more details about the warm inflation scenario. So in warm inflation, then we have these interactions of the influent with other degrees of freedom that generates dissipative effects, radiation production. And this radiation production, of course, is going to back react on the influent dynamics. For example, this changes that radiation, the dynamics of the radiation energy density. It can have a source term for the radiation here. Upsilon here is actually models these dissipative effects during warm inflation. And you can have a regime, of course, this can stabilize, radiation energy density can be stabilized. And this gives a condition then in terms of the dissipation coefficient that we can compute precisely. I'm going to talk about that in the next few slides. And this radiation energy density then, once it's stabilized, you have a radiation energy bath, right? The influent dynamics is proceeding in this radiation energy bath. So that's one of the main difference that we have in context of with cold inflation, for example. And the influent dynamics also gets modified by this dissipative term. You have a friction term there that describes then how the influent interaction with other field degrees of field and back reacts on the influent dynamics. And usually we measure the effectiveness of warm inflation in terms of this quantity Q that's defined by this dissipative term that appears in the influent equation of motion, for example, divided by 3 times the Hubble parameter. And we can have different regimes of warm inflation depending on Q is smaller than 1 or Q is larger than 1. And we can distinguish cold and warm inflation depend on the temperature of this radiation bath generated during inflation. If the temperature is smaller than Hubble parameter, that's what we call cold inflation. That's the cold inflation regime. Otherwise, if the temperature is larger than the Hubble parameter, that is what we call the warm inflation, right? And the regime that determines the warm inflation is exactly when this radiation energy density thermalized, and if it thermalizes with a temperature that's larger than the Hubble parameter, that's the warm inflation regime. So one main difference with respect to the fluctuation, the perturbations here, compared to cold inflations, is that all the adiabatic density fluctuations can be sourced entirely by thermal fluctuations, right? Classical fluctuations, opposed to what happens in cold inflation, where the adiabatic density fluctuations are sourced by quantum fluctuations. Here, since we have the presence of this thermal bath, all the adiabatic perturbations end up being sourced entirely by classical thermal fluctuations. So when we compute then the perturbations of the influent, for example, you have a thermal component there, and the part also that also depends on the dissipative coefficient, and essentially this can dominate over the quantum fluctuations. In this regime, this is what is going to happen, right? In warm inflation, we have the adiabatic density fluctuations sourced by these classical fluctuations. So that is one important difference compared to cold inflation. So how we build then warm inflation, right? How we do a model build and then based on particle physics. Since of the beginning of warm inflation, we already learned that was something hard to construct. It is not. It can be easy just to say, right, that we have these dissipative effects and this is going to generate a radiation bath, and then that's going to change the influence on dynamics, but that's not so easy to construct microscopically. So we think, for example, coupling the influence to light particles, right? It could be fermions or the scalars. I put here a Yukawa type of interactions, where the influence is direct coupled to radiation fields made, for example, of fermions. So we know from quantum field theory that this is going to generate, right? If you are in a thermal bath, this is going to generate a thermal corrections to the influenton field. In particular, it's going to generate large thermal mass corrections to the influenton. And these thermal corrections, for example, the thermal mass correction can be much larger than the Hubble parameter. So what this end up doing for the dynamics is just disrupting the inflationary regime. All those conditions that you need for inflation to happen, slow roll conditions, just end up disrupting all the inflationary slow roll conditions for inflation because of these large thermal corrections that can come from these couplings of the influenton to other light particles, for example. So you can say, well, that's no problem. In principle, we could work with very small couplings, right? Very small couplings would generate very small thermal corrections. But on the other hand, auto-dissipative effects are common exactly from this type of interactions. If you make these couplings very small, auto-dissipative effects are going to be very small. So that also prevents warm inflation to happen. It will be just cold inflation. So even though we can get around with these large thermal corrections working very small couplings, this is going to result in very little dissipation. So warm inflation is not going to happen. It will be just the standard cold inflation at the end of the day. So how we get around with this issue? We have specific models that we constructed that can go around this problem. One of the first models that we have constructed is what we called the two-stage decay model, where we still have the influenton coupled with all other fields, but the influenton only couples directly to heavy fields. And these heavy fields can be then coupled to light fields, to radiation fields that can be bosons or ferms, whatever. So you can model, for example, this type of interaction. It is still very standard in particle physics, right? You can have your influenton field with some potential. And the influenton field can be coupled to these heavy fields, right? And the heavy fields coupled to additional light fields. So this avoids this problem of having the influenton directly coupled to radiation. It is only coupled indirectly to radiation. So this has several advantages, and this is a model that warm inflation can work in this context, provided these heavy fields has a mass much larger than temperature, for example, and the light fields are radiation fields with a mass much smaller, for example, compared to the temperature of the produced radiation bath during warm inflation. So this is the same type of interactions, right, that we find, for example, in preheating, reheating, cold inflation. But now we are exactly taking into account the effect of all these interactions. So how this works, right? If we couple the influenton to heavy fields, so we are decoupling the influenton to the radiation bath. So we are avoiding essentially the influenton to receive all those large thermal corrections. So this is not going to disrupt, for example, the inflationary regime. You can still have inflation happening here, even in a thermal bath. And since the influent is coupled to heavy fields, the thermal corrections that this heavy field is going to give to the influent on potential, for example, is going to be all Boltzmann suppressed, right? Since they have a large mass, much larger than the temperature, all the thermal corrections are Boltzmann suppressed. So this actually prevents the influent on to receiving large thermal corrections. And the heavy fields are only coupled to light fields. So it's this decay channel then of the heavy fields decaying to light fermions of scalars that's going to give us the dissipative effects that we need in warm inflation. So here we have then the influence on the couplet from the radiation. We can manage to have rather large couplings here. It can be order 1, for example, no problem. And of course, you could start worrying about the quantum corrections then to the influent on potential, for example. But this quantum correction can be mitigated, for example, or reduced if we build this type of interactions in the context of supersymmetry. In the context of supersymmetry, you are going to have then both bosonic and fermionic that can cancel between each other or almost cancel in context of the inflation. And that is sufficient to reduce these vacuum corrections that could come, for example, from these heavy fields. That's why we can work with other large couplings, for example, and not worry with the quantum, either quantum or thermal corrections to the influent potential. So this is a model that we have shown that that can work with warm inflation, that we can precisely construct in the context of warm inflation. Of course, we can study all these type of interactions and which sort of dissipative term is going to produce. Then we have done that earlier reference and study all possible interactions of this influent on field could have to bosonic or to fermionic interactions and all the types of interactions, depend on the type of interactions of this, the influent on field to these heavy fields to the light fields that could be either bosonic or fermionics. We can compute that precisely in quantum field theory. What dissipation coefficient would be generated, and the Leiden friction coefficient that arrives then in this regime of the temperature be much smaller than the heavy fields, end up being dominated by process like this, where the influent on field is interacting with these heavy fields. These heavy fields are essentially decay into light fields, and that is all bosonic. Is exactly coming from bosonic type of interactions that gives the dominant type of dissipation. And it goes something like this in terms of the different coupling constants of the parameters of the model. And of course, if we are considering the temperature much smaller than the mass of these intermediate heavy fields, this dissipative coefficient is still rather small. And one way to make this dissipation coefficient sufficiently large is, for example, to work with a large number of fields, both heavy and light fields, that can be motivated, for example, in string theory, Brenes, that usually you have a very large number of fields, right? So that's one of the motivations, for example, for this type of system that we have that can be motivating both in the context of supersymmetry and originate from a string theory or Brenes, for example, a Brenes theory that we have a very large number of fields. But it's still kind of awkward, right, to have models with a rather large number of fields. So we then have another model that gets around this problem. That's what we called the warm-Liro influent model that was published in this reference some time ago. And here the idea is much simpler. it's actually a much simpler and a very nice idea that motivates, for example, from extensions of the standard model of particle physics. Here, for example, you can have two complex scalar fields that I called phi1, phi2 here. And these two complex scalar fields are charged under the same gauge group, for example, U1 gauge group. So they are charged under the same gauge group. So you have two phases for these fields, right? For phi1 and phi2, but only one phase, that is the true Nambu-Goldstone boson, that after symmetry breaking, after this symmetry is breaking, end up being eaten by the gauge field. But you are still left with another phase for this complex field. And this other phase remains as a physical singlet in the singlet scalar in the theory that we can make to be the inflaton field. So that's the motivation for this type of model. This extra phase of one of these scalar fields end up being the inflaton in our case. And the motivation for this type of model, as I mentioned, it comes from extension of the standard model. For example, there is this extension that's called the little Higgs model, where the Higgs is exactly associated to one of these phases of these scalar fields, like a pseudo Nambu-Goldstone boson. And the Higgs then is naturally protected against the large quantum corrections, right? This kind of solve the hierarchy problem that we have in the standard model of particle physics. So we just took the motivation from this extension of the standard model in the context of inflation, and these complex scalar fields with this extra phase works nicely in the context of warm inflation. So here, for example, we can have the inflaton coupled into both charged and singlet biofermions with interactions like this, for example, that obeys this interchange symmetry, or sometimes called in the context of the extensions of the standard model as a sort of mirror symmetry. And we can build this type of interactions. And we just substitute here those complex scalar fields that we have here. For example, this phi is the phase that remains after the extra phase is eaten by the gauge field. We end up with an interaction with fermions, for example, like this. So this fermion mass end up being bounded and can be light, right? Exactly because of this structure that end up appearing here in terms of trigonometric functions, in terms of this scalar field. So this prevents exactly all those problems of generating large thermal and quantum corrections to the inflaton field. We can now couple the inflaton directly to light fields. And because the mass of these light fields can be with appropriate, choosing appropriate parameters here, it can be bounded and be made light. So we can compute what would be the dissipation coefficient in this case, even though this type of interactions end up canceling both quantum and thermal corrections. It's not going to cancel, for example, non-local corrections that end up generating auto-dissipative terms that is important for the dynamics. For example, we can compute, for example, what would be the dissipation coefficient for those type of interactions. End up being something like this. Gamma here is, for example, the decay width of those fermions to additional light fields that we can have in the model, for example, that obeys that type of symmetries. And you end up getting a dissipation coefficient in terms of the different parameters of the model, coupling constants, for example, and the temperature like this, it goes linear in the temperature. So this is one example. Another example of this dissipation coefficient that we can compute precisely in the context of particle physics, for example. And we have another version of this model. Instead of coupling the inflaton to those scalar fields to fermions, for example, we could couple it to scalar fields. This is what we call it the warm little inflaton scalar version. So we have the same sort of structure, just replacing the fermions there by additional light scalar fields that I'm called chi here, and with the same type of interchange symmetry, right, or mirror symmetry. And with this type of interactions, we can compute again what would be the dissipation coefficient for the inflaton in this case. And we have then, in the case of fermions, we have that dissipation coefficient. Now, with the inflaton coupled, for example, also to scalars, that is the type of dissipation coefficient that we end up getting. It's a little bit more complicated, but we still can compute it in quantum field theory. And with the different parameters here involved the coupling constants and parameters of the model, right, that end up appearing explicitly in these dissipation coefficients. So this is the third model that we have that works very nice in the context of warm inflation. And there is this other model too that is called the minimal warm inflation model that was proposed by these authors, Berghaus, Graham, and Kaplan, some time ago, not so time ago, where now the inflaton is, for example, an axion-like field, right? Axions are very well motivated in context of particle physics, is one of the solutions, for example, of the so-called strong CP problem in quantum chromodynamics. And axions can couple it, for example, to Yang-Mills fields like this, like with a kind of Sher-Symes type of coupling. And alpha G here is the fine structure coupling constant for this Yang-Mills field. F is what's called the axion decay constant in standard axion physics, for example. And this is a very standard type of interactions that we find in axion physics, right? Axions can be, as I mentioned, is well motivated type of field. That can be, for example, there are models that propose axions as dark matter, axions as a possible dark energy, axions for inflation. And here is following the same idea, right? Now we have this axion that's going to be the inflaton for us that's coupled to Yang-Mills gauge fields like this. And this type of interactions, right, generates a friction term that has been computed before in the literature in the context of axion physics. This friction term can be related to the Sher-Symes diffusion rate, and it goes something like this, with a coefficient that depends on the couplings, the number of the colors that you have for the gauge field, the number of fermions, if you have fermions, the flavors of number of fermions, alpha G, the coupling constant here, and T to the power 3 divided by this axion decay constant square. And the nice thing here is that the inflaton is also protected from these thermal and quantum corrections. Since the axion is a pseudo-Nambu-Goldstone, it has a shift symmetry. And this symmetry just protects the axion to receive, in this case, the inflaton to receive both quantum and thermal corrections. So it's naturally by the symmetry again, because of a symmetry, you don't need to worry about these large thermal and quantum corrections. So this is another model that works very nicely for warm inflation. So another extension of this minimal warm inflation is in the case if you have also fermions in the system. If you couple those Yang-Mills fields to chiral fermions, for example, that changes that dissipation coefficient that is coming purely by Sphaler process, that is in the context of Yang-Mills theory, and end up they kind of suppress but not vanish the dissipation coefficient, provided that you have chiral fermions there. Gamma here is the rate of rate for these chiral fermions. So this has been computed when you have fermions also in the system, end up being modifying that dissipation coefficient here that's purely by Sphaler process in a Yang-Mills vacuum in a thermal bath, end up being changed by an expression like this. And you can also take into account the effect of Hubble expansion, right? And then you have a Hubble dilution in the context of cosmology that also changes that dissipation coefficient that has been led to a different form for the dissipation coefficient in terms of that Sphaler decay rate that also appears here. But because of the Hubble dilution, that rate end up being modified. So this has been studied recently by these authors, and we also have studied more precisely this type of dissipation coefficient in context of warm inflation. So one important problem now, of course, we have these all different warm inflation models, right? How we connect with the observations. We need to compute the power spectrum, right? How the scalar power spectrum for this model is going to change, right? Because of these dissipative and thermal effects. And we have computed that, or in the context of warm inflation, we have a kind of analytic expression actually for the power spectrum in warm inflation. The first term here is the standard cold inflation result. And what warm inflation does here is exactly to modify this cold inflation result by the thermal and dissipative effects like this, right? Q here is again that quantity that I have defined at the beginning, is that the dissipation rate divided by 3H, the Hubble parameter. And here is if you assume that the perturbations of the influent are thermalized, then that changes also the statistics here, right? For these perturbations end up entering a kind of Bose-Einstein contribution here because of the presence of this radiation bath. So this is how, how the power spectrum in context of warm inflation gets modified. And there is additional factor here, this GQ here, that even though these first terms can be computed analytically, this term here, we can only estimate it numerically. So it's something that is computed numerically, is something that we cannot compute analytically. Sorry. So that function GQ then accounts exactly for this effect of having the influenton in this thermal bath. So you have the influenton perturbations in this thermal bath. You have also the perturbations of the radiation bath. And so both influenton perturbations are coupled to radiation bath, to the perturbations of radiation bath. So that function GQ here exactly accounts this effect of this coupling of the influenton perturbations with the radiation, the perturbations of the radiation bath. And for different forms of the dissipation coefficient that I have mentioned before, for example, if the dissipation coefficient is something linear in temperature, or something that goes to cubic in the temperature, we can compute numerically that function GQ and produce a fitting, right? Produce a fitting, a numerical fitting for that function. So depending on the dissipation coefficient, we have different fittings for that function GQ. But this type of fittings, of course, we compute then in some specific regimes, right, for small dissipation, large dissipation. So it is valid only on some specific regimes. And how we get around this, we need some more detailed form to get this function GQ. And we have produced softwares, more recent softwares that exactly compute this GQ precisely, that I'm going to mention for you in a few slides. One of these codes, for example, which is code that we have released last year. That is a code in Mathematica that exactly solves the full coupled system of perturbations equations in warm inflation and generates the appropriate the function GQ that we can then insert here in the power spectrum. And once we have that, we can compute out the observations or observational quantities that we can obtain in the context of inflation or warm inflation. So once we have that, we of course need to compare these results to observations, right? We can compute, for example, this ratio, that is the tensor perturbations divided by the scalar perturbations. That is the tensor to scalar perturbations. That's something that can be, in principle, measured through the CMB observations. As I mentioned before, we don't have a measure yet of this quantity, only an upper bound. So depending on the inflation model that we have, we can compute precisely this quantity. And from the power spectrum, we can also compute the tilt of the power spectrum. That is the spectral tilt, NS here. That's another quantity that is kind of very precisely obtained through CMB observations. So that's a way to constrain inflationary models, for example, through the computation of this quantity and comparing it to observations. So once we have the power spectrum, right, for the scalar power spectrum here in warm inflation, we can come back here and compute all these quantities that are relevant for observations. So we need to, as I mentioned to you, to precisely obtain this function GQ, we need to solve the complete set of perturbation equations in warm inflation. So that have two parts. We start, for example, from a perturbed Friedmann-Lemaitre-Robertson-Walker metric. That's the fully perturbed metric then. Alpha, beta, phi here are the perturbations of the Friedmann-Robertson-Walker metric. And in the context of Einstein equations, we can compute then thematic equations, right? You have these perturbations of the metric are determined then by these evolution equations. And then in warm inflation, we have also the perturbations of the inflaton field, the perturbations of the radiation, right? And this is also coupled to the perturbations of the momentum of the radiation that is present in the context of warm inflation. So we end up getting a full set of evolution equations like this that need to be solved with the metric equations, like the full set of coupled equations that we need to solve. And because of the presence of dissipation, right? Remember, for example, in standard statistical physics, from Langevin equation, the Boltzmann, for example, the Langevin equation that models, for example, Markovian dynamics, right? Because we have dissipation, we know that there is always associated a stochastic forces, right? Stochastic terms. So in the perturbations equations for the inflaton, besides the presence of dissipation, there is also a stochastic noisy term there, similar to what we have in Langevin, Brownian motion, for example, that we always have a fluctuation dissipation theorem, right? Dissipation is connected to a noisy stochastic term. So that changes the perturbations equation then. not it's not deterministic, but end up being stochastic type of equations that we need to solve for the perturbations in warm inflation. And these stochastic terms satisfies a kind of a dissipation fluctuation theorem with a 2-point correlation function, like, for example, we have in a Langevin equation. So we have to solve this full set of perturbations equations that's not deterministic, but are stochastic for warm inflation. And we can also work out, instead of working a stochastic system of equations that might be much harder, we can work, for example, with a Fokker-Planck implementation. We choose, for example, a gauge, appropriate gauge for those metric perturbations. For example, we can fix an appropriate gauge. Here I'm fixing the gauge to be the uniform curvature gauge. So we end up an equation for the inflaton perturbations, radiation, that moment perturbations. We can write that those stochastic equations in a form of a matrix equation, like this, for example, put it in a form of a matrix form. This is still a stochastic equation. And the definition of the power spectrum is defined in terms of the 2-point correlation function of this quantity here that I end up putting in this matrix form. And this 2-point correlation function can be associated to the probability density that comes from the solution of a Fokker-Planck equation, right? So we can transform the stochastic equation in a deterministic computation for the primordial power spectrum, that instead of working with a complicated stochastic system, end up being a deterministic system now in terms of this Fokker-Planck implementation. And here, once we have this probability density, this 2-point correlation function for the perturbations end up being determined by an equation of motion like this, in terms of these matrix elements A and B that we can read directly from this complicated system of equations, right? So we end up solving a deterministic matrix equation at the end of the day. So this is a much more convenient way to solve for the perturbations in warm inflation. Anyway, in earlier codes, for example, that we use the stochastic system, usually we make use a combination of Mathematica or Maple software to first generate appropriate background initial conditions. And then we solve that complicated stochastic system that's much more convenient to put in a machine kind of code like Fortran or C or Python. Fortran and C can be much more efficient than using Mathematica or Maple to solve stochastic equations. That is much more time consuming, and it's much better to solve in a machine kind of software like Fortran or C to run these stochastic perturbation equations. And then that generates the power spectrum, right? That we can then produce fittings for that function GQ. And once we get this GQ, we go back there to the form of the power spectrum, insert there. And then we can again use, for example, Mathematica or Maple to just use symbolic computation to run for the background again, normalize the spectrum, compute observable quantities important for comparing with the CMB quantities, for example. So it's kind of a hard process, and in particular to obtain again this function GQ. So more recently, these authors come up with a software, a Python software, which is dedicated to compute that GQ function. And we have proposed last year this code that's a purely Mathematica code that's much easier to use. that is actually to implement this full procedure, but instead of solving for the stochastic perturbation equations, we solve for the deterministic equations. That is much easier to do in the context of Mathematica. For example, it's much more efficient to solve a deterministic equation than a stochastic equation in Mathematica. So which is entirely built in terms of Mathematica with easy commands that implements all this procedure to compute the initial conditions, GQ, run the perturbations, and obtain all the observable quantities that we compare to observations, for example, for different models of inflation and different potentials. So it has an interface like this. When you run the Mathematica code, it presents you an initial interface like this, where you input your potential, can be any form of potential that you like, a large field models, small field models of inflation, hybrid models, whatever model of inflation for the influence on potential that you want to use. An initial normalization for this influence on potential, specify the shape of the potential, if it's a large field, a small field, or a hybrid type of model. Define, for example, different coupling constants that your model might have. Give the form of the dissipation coefficient. You just input here the form of the dissipation coefficient. Can be any form of the dissipation coefficient that you is going to just accept any form, and other parameters that the model might need. So it presents you with this easy type of interface, and then you just run easy commands to automatically implement all the dynamics and give you, at the end of the day, the results, right? The results that you can compare with the observations. For example, one of those models that I have mentioned to you before, for the minimal warm inflation in the presence of Hubble friction, where you have a complicated type of dissipation coefficient like this. Epsilon here, it's the decay rate due to these Faleron rates. That is a kind of a complicated type of expression. Anyway, that is no problem to insert in the easy code and run the code. For example, we are choosing here a simple quartic potential for the model, and we are connected with standard model with the strongly coupling of the gluons, for example, that is given by this type of coupling constant. That's one of the interesting things about this model. It can connect warm inflation directly to the standard model, where those gauge fields are simply the gluon fields, right? And then we just run the code, and then it's going to give you results like this for the spectral tilt as a function of that Q, that radio Q, that is the dissipation coefficient divided by 3H. So for different values of this parameter Q, that depends on the dissipation coefficient, parameters, etc. You are going to get results like this one, for example, right? For the spectral tilt, for the tensor to scalar radio, and then we can compare with the observations. Here we are comparing with the data from Planck, for example. We have 1 sigma and 2 sigma regions for the tensor to scalar radio in terms of the spectral tilt. And the CMB measurements gives this type of constraints, then 1 sigma and 2 sigma constraints for these quantities. And we can just compare with the results that we get, at which point here corresponds to one given value of Q, right? So this constrains to how large can be this parameter Q that fits the observations, essentially. And that constrains, again, the type of parameters that we have in the model. For example, the axion decay constant is going to be constrained by this type of analysis. So we are constraining the microphysics when you compare with the observations. And this is another example that I have mentioned to you, that the warm little influencer model, that we are combining both the Fermi interactions and the scalar interactions with the influencer field that generates then a more complicated type of dissipation coefficient that combines the two types of dissipation coefficients essentially. That is going to, one or the other is going to dominate, depend on the choice of the coupling parameters that we have in this model. So we have a sort of, again, very complicated dissipation coefficient. That is no problem. We can insert that in the code and just run and get results like this. Depend on the choice of coupling parameters that we have. And again, this is constraining, again, the parameters of the microphysics based when we compare with the observations, right? So that's one way to explicitly constrain these different couplings and parameters of the model based on this comparison with the observations. And this that's what with too easy, right? The code makes it possible to implement in the context of warm inflation. So essentially, we can implement any form of potential and any form of dissipation coefficient and analyze that and compare with the observations. So not to extend too much, just really give you my summary then. I finish here. So we have that these non-equilibrium dissipative effects that comes from the microphysics, right? When we insert, embed inflation in the context of particle and quantum field theory, this generates these non-equilibrium dissipative effects, and these effects, thermal and dissipative effects, end up changing to what we observe, right? Quantities that we need to compare with the observation. So it modifies the inflationary predictions. And by now we have different working models for warm inflation that is explicitly based on well-motivated particle physics models. For example, the ones that I have shown to you that are kind of well-motivated type of models, either in string theory or in extensions of the particle physics of the standard model, or even motivated by the standard model itself. And we have developed this new, we have now these new high precision numerical codes that are able to automatize and popularize warm inflation applications and make it much easier to work with warm inflation nowadays than in the previous days that all this machinery was not available for the public in general. So thank you very much. I finished here.
Okay. Thank you very much, Professor, for your very nice seminar. Are there any questions? Do you have questions, the students and colleagues?
I got one question. You want it?
Yeah.
Yes, you can. Please.
Okay. First of all, thank you for your nice presentation. I was wondering how sensitive your results are to the precise microscopic derivation of the dissipative coefficients, particularly regarding the assumption entering the Spheleron rate.
You mean, for example, that depends on how precise we compute these friction terms, for example. Yes, usually we work on some specific regimes. For example, in a high temperature regime, where in quantum field theory, we can manage the computation of these friction type of terms, right? That is much easier to compute in the context of quantum field theory. And for example, for Tesfatheron, right? As I mentioned to you, there are different expressions or approximation, let's say, for Tesfatheron rate. And this result comes, for example, with high precision lattice field theory. That's a non-perturbative quantity, so it's very hard to compute, for example, analytically in general in quantum field theory. People usually use lattice field theory, but it's very precise again. And so of course it might depend on how precisely is going to be this coupling constant and dependence here. So that there is a dependence there. Of course, the more precise you obtain your dissipation coefficient, the more realistic will be the comparison with the observations, right? So it's precise up to the approximations used to compute these dissipation coefficients that I have mentioned to you. So provided you are in that regime where these computations are valid, it's valid, it's precise. If you go in a regime that is outside and then you have to recompute these dissipation coefficients, like for example in a small temperature regime that is far from the high temperature regime that you use to compute that, and then that you have to recompute things to get the appropriate dissipation coefficient, for example.
Thank you.
Thank you, Joyce. Thank you, Professor. Any other question?
No, Professor.
Yes.
No, I don't have a question.
Okay. Professor, I think my question is about the current observational data about inflation. We
Yep.
know we have data coming from, for example, DESI,
Mhm.
DESI combined with Planck. And then some potentials now are disfavored, like for example, even the Starobinsky model is disfavored now, but it can be including these war inflation effects, dissipative effects. Can we put these potentials inside again into within the observational region?
Yeah, sure.
Is possible?
For example, I gave you two examples here that does not work with cold inflation. A quartic potential in cold inflation is just is already completely outside the scope of cold inflation. Almost all simple potentials that we have that is well motivating particle physics, right? A quadratic potential, a quartic potential, or a kind of symmetry breaking simple potential, renormalizable potentials, right? That is well motivating particles are all just not compatible with warm inflation. But in warm inflation, it just fits very nicely because of the thermal anticipative effects. For example, the quartic potential, you can put it just nicely inside the Planck regions, for example. I gave you another example here with a quadratic potential that is already not favorable by cold inflation. But in warm inflation, depending on the dissipation coefficient and the coupling constants and so on, it can be just nicely become compatible with the observations again. So all these simple potentials become compatible with the observations in the context of warm inflation. And you mentioned, for example, the recent data, right? I think you are, for example, the Atacama Cosmology Telescope, right? The last year data from ACT. It's given by this purple region here, right? The orange region are the old Planck data, and the most recent when you combine DAISY, BAO, from all to those measurements and the most recent measurements from ACT, this shift the curve, the confidence levels to the right? So you are saying that the Starobinsky would be very nice compatible with the Planck data, but with the ACT data is already kind of outside the 1 sigma, 2 sigma region, right? So, but again, with warm inflation, that's no problem, right? Depend on the dissipation, coupling parameters, and so on and so forth. Even the simplest potential, like a quadratic potential, we can make it compatible either with the Planck data or the most recent ACT data, for example, as we see here.
Okay. Professor, another question is about the reheating. Just during inflation, the universe is cooling, and then we require reheating
Yeah.
to put temperature, no, in the universe,
Yeah.
to be in agreement with the following post-inflationary phase. And
Yeah.
now you have war inflation. Then,
Yeah.
from the point of view of war inflation, it's not necessary to include
No,
reheating.
exactly. You can end the inflation automatically in a radiation-dominated regime. So there is no need in principle for any reheating. You already end the warm inflation in a radiation-dominated regime. So that skips completely the reheating or preheating, whatever, post-inflationary regime to generate this radiation bath, right? Because since you already have this radiation bath being generated throughout the inflationary regime, you can just end inflation in a radiation-dominated bath at the end of inflation. So it's just connect the end of inflation with the Big Bang dynamics automatically.
Okay, and the last question is, are there any open problems currently in war inflation, like theoretically or yes?
Yeah, there is a lot of things because you can come up with other models for warm inflation, right? Because all these results depends on the specifics of the microphysics that you have. So you can have the other proposals for whatever fields that you have there coupled to the influenton, right? Of course, you need to be careful to always avoid these large quantum thermal corrections to the influenton potential. So that is going to always to constrain the type of microscopic models that you can use. But you can have many other types of models. And as the colleague was saying, these results also depends on the precise determination of these dissipation coefficients. So depend on the regime that you are studying, you can have other forms of dissipation coefficients. And then you have also, we are now working with non-Gaussianities, for example, in the context of warm inflation. We have previous studies concerning non-Gaussianities, but it still needs a lot of work to study all these different modules in the context when you extend beyond the first order perturbation equations, right? You go to determine the bispectrum and compute non-Gaussianities, for example. That is another thing that's kind of sort of open. So there is a many open problems in the context of warm inflation that's still worthwhile to study.
Okay.
Just like in cold inflation, right? All the time somebody's coming with a new inflation model, a new cold inflation. We can come by with some new warm inflation model.
Yes. And about the primordial gravitational waves, I think.
That's another. Yeah, that's something that we have been trying to study, right? Because, right, if you look at let me go back to the power spectrums again because it's very, very elucidating. You have the power spectrum, the scalar power spectrum from cold inflation here. And here the power spectrum, the corrections to the power spectrum come from dissipative effects. And you see this GQ here, depend on the module, it's something that is growing with Q, depend on the module. So this end up giving you a power spectrum that grows with the dissipation coefficient Q, right? And of course, we evaluate this at some pivot scale where we compute out to the CMB quantities and so on. But during inflation, this Q here in general is growing. So this scalar power spectrum as inflation proceeds, the power spectrum is growing. So that can be important for gravitational waves and primordial black holes, and that is something that we have been studying now too. Depend on the type of model that we have.
Okay. Thank you very much, Professor. Any other questions? Okay. Perhaps, Professor, if some student has a question, he can write you. I don't know, you have...
Yeah, sure. Just email me.
Possible.
Yeah,
Okay. Okay, Professor, then thank you very much. And we are in touch then. I'm going to try to to give information about the Congress. And then
yeah, sure.
I would like to be
Yeah.
yes, we are going to be very glad, no, if you can come here to the Congress and share with
Thank you very much.
your
Very
knowledge.
nice. Yeah.
Yeah. Thank you, Professor. And then, yes, we can finish now the seminar, okay?
Okay.
Goodbye for everyone.
Thank you again for the invitation.
Yeah.
Thank you, Professor.
Bye bye. Thank you.
Thank you.
Bye.
Thank you.
Bye.
Thank you, Professor.